Hello, everyone. Um, I am Thiago and I'm here with Blake, and today we're going to present our project, Search and Commit Multitask Belief Space Planning. Um, so the challenge that we're trying to solve is that most of the time in the real world, things can be much more complicated than they actually is. And we're focusing mostly on perceptual uncertainty. Imagine, for example, noisy sensors such as sliders and cameras, they might suffer from inherent noise or domain shifts or even occlusion, as you can see in the image on the right. But also, it's important to understand that traditional planners, they assume exact state knowledge, which is a deterministic failure for a couple of problems. As a consequence, planning on noise estimates can lead to very, very problematic scenarios. For example, in the setup that we've done, we have the following. Uh, it's an object, a mustard bottle that is being picked. The RT does not take into account the uncertainty and fails in the picking. The learning design goals for this project is first to understand and handle uncertainty by explicitly reducing uncertainty as we go before committing to the action. And one of the goals that we have for this project is maximizing task completion rate, but also maintain a collision-free trajectory, and most importantly, formulate the framework to be modular. Our approach is to go of like pick and place mustard bottle in the go bin. And the way that we model uncertainty is by having initial uncertainty, for example, around the bin itself, um, of 50-50 initially of where the mustard bottle might be. And then we try to predict the pose of the mustard bottle in the XY position. So we also introduce uncertainty in that regard. Um, if we predict the right bin, as shown, this is the uncertainty that we have around the exact position for the bottles. Our customer approach for this problem is to have two different regions, the light regions where you can collect perfect measurements. And in the bin light region, for example, in the dark measurements, anywhere outside that, we're going to get a Bernoulli distribution, which is going to give an observation of 50% of whether the bin is correct or not. In the larger measurements, we're going to have a Bernoulli of 0.8, for example, if the object is indeed in the bin that we select, and 0.15 if the object is not in the bin that we select. For the pose estimation, the pose light region, the dark measurements is going to be an infinite noise, Gaussian, if it is outside the light region, and a very, very small noise of 0.01, the identity matrix in the light region.
So the solution design that we ended up going with was most notably using the rapidly exploring random belief tree published by Brie et al. In 2011, which we will refer to as RRBT. So in phase one, we do that first search, RRBT based search to reduce uncertainty about which bin the object is in, execute that plan, and then do another round of RRBT to reduce uncertainty about the object's position, covariance, execute that plan, and then we commit and perform the pick and place. Now here's a demo of the system in action. So first it plans and executes to reduce its uncertainty about which bin the object is in. You can see it correctly now chooses this and activates the perception system to collect a point cloud and do ICP to get a pose of the object, and then goes to the second light region to reduce this uncertainty that we instantiated in here about its XY position. And then since it went to that second light region, it reduced its uncertainty, was then able to successfully plan a grasp, pick it, and place it in the goal box. Okay, so a quick note on the evaluation of results. The RRBT base system that we just described was able to complete the task 90% of the time, whereas the baseline that did not have the ability to plan and execute that plan to reduce its uncertainty only completed the pick and place task 10% of the time. But the baseline you can see made much more mistakes, primarily because the when it was able to select the right bin and not be in that failure mode, the grasp-related failures came from the uncertainty in the position where it would plan to make a grasp the wrong position, and therefore not complete the task. And then Tiago, you want to jump in and do this?
Yeah. The design experience that we got, a couple of things that we can take away from the whole project Is a couple of challenges. First is how to model noise and like mostly understanding the underlying belief update dynamics and what to plan over. And that includes, for example, what kind of filters we have for the noise and things of the sort. But also managing complexity. It just so happens that designing a fully integrated system in Drake for uncertainty simulation and setting up things like this is actually pretty complex. But there is a bunch of learning as well. Simplicity versus efficiency trade-off in the sense of like we're trying to achieve a suboptimal path that, for example, we're first exploring and then actually committing, is way easier and more scalable than actually optimizing for the full like spectrum of the task. And also this hybrid architecture of switching between planners is a powerful way to be a very modular task completion setup.
Great. Thank you very much. If you have any questions, you can ask them in class, and our code is available here on GitHub.